and he's a senior scientist and group leader at the Max Planck Institute for Plasma Physics. His interests are focused on active learning methods, Bayesian experimental design, uncertainty quantification, and inverse problems. And today he's going to give us a talk on uncertainty quantification, surrogate building, and active learning. So thank you very much, Udo, for joining, and looking forward to your talk. Thank you.
Yeah, it's a pleasure to.
So why don't you share your screen?
Yeah, coming.
There you go. Okay. You
Okay.
can see it.
Yeah, so it's a pleasure to be invited and to be able to provide an overview about tools and approaches to uncertainty quantification and active learning. And it's an actively developing field, so I think there are quite some interesting developments going on. The presentation has been built on results and slides from quite a number of people, which I'm very grateful for. Okay, short outline, and let's get started. Why do we care about uncertainty quantification at all? In principle, if we would be able to perform experiments for all our needs, then we would be in a pretty good shape, because for actual experiments, the practices about how to quantify uncertainties, how to perform test experiments are highly developed, and so the experiments still provide the gold standard for establishing cause and effect relationships. Unfortunately, this is not always possible. On the other hand, we have simulation experiments where essentially the description is pretty vague, especially in the biological systems, where we just look for trends. And then there's something in between, which I would call computer experiments, which we are mostly dealing with in physics and in especially also fusion. And we perform experiments using these computer codes, complex computer codes. Sometimes an actual physical experiment is really not an option, because we cannot handle the parameter ranges. It's too expensive, too time consuming. The number of potential variables are just too large to perform expensive or exhaustive experiments. And there may be also ethical considerations. If the actual experiment is not feasible, then of course computer experiments can provide a way out, given that we have adequate understanding of the equations which are used, that we are sure that these equations are correct, and then of course the computational time has to be manageable. However, manageable is pretty wide range of, let's say, extending up to several months per single one. So what do we often see in fusion, but also in other situations? Plots like the one which is shown here. We have simulation data and experimental data. Typically, the experimental data are associated with error bars, and then we have some modeling results, and then there are statements like the data and the model are in good agreement or in a bad agreement. And actually, this could be kind of a density profile as function of radius in a tokamak, where the data points are from Thomson scattering or reflectometry, and the dashed line could be from simulation. However, actually, we are lacking information. Is that really a good match between the experiment and the simulation? Because we don't have any uncertainties assigned to the simulation. If you ask the modelers why they do not provide uncertainties, which are by default requested from people performing experiments, then typically the answers are, oh, there are so many input parameters, it would be impossible to come up with uncertainty estimates, or we are not sure if the model is correct in the first place. It's more about the trends. But this is, of course, something which is not a pretty nice situation, because if we cannot associate uncertainties with simulation results, then of course we are also lacking all subsequent tools, like which of these two different data sets provides more information, for example, for the parameters used for the simulation, which are more constraining. So to make progress here, one should really undergo all the possible attempts to associate also simulation results with uncertainties. And fortunately, the situation has changed in the last years, and we are now approaching a state where this is actually not only a dream, but can also be realized. In fusion, this, let's say, lack of information about the uncertainty of simulation data has also triggered some intense discussions. Here I've shown a picture from a publication from 2009, where the transport by ion gradients is displayed as function of radius, and what has been claimed is that the simulation results cannot adequately describe the experimental results, because at some position of the radius, at R 0.7, there's a huge discrepancy between the simulation results and the experimental data. So the experimental data, the solid line, show a large discrepancy with the red bullets, and then there was the claim that the theoretical model underlying the simulations is not capable of explaining the observed trend. And of course, that would be a pretty severe situation, because that would mean that we are missing some crucial information. However, after quite some joint effort, it turned out that the simulations were pretty sensitive to information, experimental input to the simulation codes about some gradients of the ion temperature. And if the experimental uncertainties were taken into account, then it was possible to get simulation results which were quite close to the observed experimental data. So the possible shortfall, which was at first considered possible by the simulation results, turned out to be not present, given that one took into account the experimental uncertainty of the input data. There were also a few other issues involved, but if the modeling results would have taken into account the uncertainty of the input, then a lot of discussions would have gone in a different way. So I think I could illustrate that the quantification of uncertainties in computer simulations is pretty important, not only, like I showed, to explain discrepancies between experiment and modeling, but also to learn about the parameters. So which parameters entering the modeling, the computer experiment, are the most important ones, which have the most interaction. How much can we believe into the simulation output? Historically, it is that in some areas, the quantification of uncertainties from computer experiments were much more prominent from the very beginning. Here, especially in the engineering field, where very early on finite element codes were equipped with uncertainty quantification measures, intrusive ones, because there, of course, you want to know if a building is stable or not. In other areas of research, it become became more prominent, driven by the military needs. So especially in the US, there was a large initiative to take into account uncertainties in modeling the behavior or aging of nuclear weapons. And to do that properly, there was quite some effort pursued. And driven by this research, then the uncertainty quantification efforts also spread into other areas. And now I think they are becoming more and more prominent. So what tools do we have to tackle that problem? Just to set the stage, very often the terms uncertainty quantification and verification, validation are almost always used simultaneously, but actually they refer to different quantities. The main problem is that we have simulations which, since these are mostly very complex models, provide approximate solutions, and we don't know the exact solution. And of course, then there are the obvious consequences of that. How good are these approximations? Essentially, the code results. What is the predictive power? And how do you test these quantities? Traditionally, there are different classes of problems which may happen. The first, most obvious one is that the model which is should describe reality is simply not good enough. So there are approximations which have to be made, for example, because otherwise it cannot be solved, that the model is just not a good representation of the actual reality. This match or mismatch between the model and reality has to be assessed in the validation step. It may be that the model is actually a very good description of the reality, but the numerical implementation is not good. So there may be approximations, there may be discretizations. It may be that the algorithm is just simply not the correct one to solve this class of problems, maybe because it's missing shocks or something like that. And this is the verification step. And then it may be that the inputs for the problem are just uncertain, so that the problem which is solved is not precisely described. And that is the realm of uncertainty quantification. And essentially, to have a proper scientific code, all these steps have to be checked and tested. This is not a new insight. And actually, one has to say that in physics, maybe one was a little bit behind. In other areas, engineering especially, that was much earlier taken up and also, let's say, standardized. Here, a graph from 2006 from mechanics, where the flow chart is essentially one has two different branches. The one is the mathematical modeling, where essentially the mathematical model has to be checked if the computational implementation of that matches the mathematical model. That's the verification step. And then at the end, when the mathematical model and the computational model do agree, then it is cross-checked with the experiment, and then this validation, this cross-checking, then is decided if it's good enough, and then the code is considered as a reasonable, let's say, approximation to the problem at hand. However, this simple approach may be too simplistic. In reality, it is presumably more like that one. I will guide you through. So we have initially a physical model of some system that maybe, if we go here to the right, consists of a pretty complex one, maybe multi-scale model, which is then transferred into a mathematical model. This mathematical model has to be adapted to the computational capabilities. And this typically involves that one has to discretize the equations, differential equations, stochastic differential equations, and come up with some implementation of the geometry, which then consists of the numerical model. And this numerical model has then to be attacked by algorithms which are suited for the computer in an efficient manner. And the results of this computer simulation then have to be verified against the underlying mathematical model. So once this is done, then the next step is to check if the computer simulation agrees with the actual experimental data. And here on the left-hand side, then we have the validation step. And this is then where uncertainty quantification needs to take place, because by the means we have uncertainties on the data, and since the computer simulations depend on uncertain input, we have also uncertainties in the computer simulation. Once this validation step is successfully, then we can go on and quantify how reliable the model is and come eventually to a decision making, which of course depends how uncertain or how reliable the model is. And if we are not happy with the validation step, then this is an indication that we have to improve our physics system. So how do we do now the validation? So I assume that the verification has been successful, so that we know what that we can rely on the implementation of our code, so that only the validation is of interest. And as illustrated with the example, for any validation, we have to come up with a measure how close the agreement between the data and the simulation results have to be. If there would be no uncertainty on the input side, then any disagreement without the experimental uncertainties would imply inconsistency. However, for all realistic cases, there is always some uncertain input into the modeling codes. And that means that we have to expect that there is a discrepancy between the model results and the uncertainties. And we can only claim that there's an inconsistency if the discrepancy between the model output, the simulation results, and the experimental data are not explained by the uncertainty which is inherent in the simulation output by the input. And for that, we need a mathematical representation of uncertainty. So many words, essentially, it turns out that we get back to something very familiar. This representation of uncertainty can be done with a familiar probability theory, and Cox has shown that this is also the only consistent calculus. So the familiar one is also the only one which is relevant. Typically, we have in the discussion two different types of uncertainties. The one is the so-called aleatoric uncertainty, which is intrinsic randomness, stochastic randomness, which cannot be reduced. On the other hand, there is epistemic uncertainty, which is due to a lack of knowledge. In practice, this difference is not really relevant, because it's often just a matter of the perspective, which uncertainty is which. For example, if you cannot model turbulence, you could consider the fluctuations as aleatoric, or you could consider them as epistemic, because if you would be able to write down the equations, then of course you could reduce the uncertainty in this respect and improve upon. Nevertheless, in practice, essentially, one can hardly avoid that there is epistemic uncertainty involved, just lack of knowledge. And that means that to be on conceptual solid ground, one has to use the Bayesian interpretation, which is essentially a probability distribution, just describes the information at hand. So there is a single uncertain value, and the Bayesian interpretation of that is that there is a probability distribution which describes our state of knowledge about this quantity. In the frequentist interpretation, P of x would be the distribution within an infinite hypothetical ensemble, but in the following, we will exclusively use the Bayesian interpretation. For the actual calculus, not much is changed. We still need the likelihood, which is also the core for the frequentist approach, but it needs to be augmented by a prior for the parameters, and essentially describes our state of knowledge before we perform experiments. If these priors are uniform, then the posterior has the same value as the likelihood. But if the prior is not uniform, then the results typically differ. What you see here is essentially always conditional probabilities. The posterior describes the probability for a hypothesis given some data and some background knowledge, and equates that to the likelihood. That's the probability of the data given the hypothesis times the prior. What you can already see from that equation is that the maximum likelihood typically does not give you the quantity which you are looking for. Typically, you're interested in the parameters which are the most likely ones given the data, and not the data which is the most likely one given some parameter. That this, let's say, flip between the conditional bars is relevant can be made pretty obvious by just seeing that if you have a non-uniform prior, the probability that you have a wet street given that it rains is of course different from the probability that you have rain when you observe a wet street, because there could be different reasons, like somebody has washed the car, something like that. So these quantities, posterior and likelihood, are commonly different. Okay, so now we have set the stage. Now let's have some illustrative examples coming from fusion. So if we consider plasma wall interactions in fusion, then one of the crucial problems is that it is an extreme multiscale problem. Many of the processes happen on atomistic scale in time frames 10 to the minus 12 seconds, but the evolution of the material undergoing bombardment and irradiation can take much, much longer. So minutes to hours and even longer. The same holds for the spatial scales, where on the atomistic side we have angstrom to nanometers, but wall elements which are eventually being used can have much larger spatial ranges, and that means that a proper modeling of these processes is extremely expensive. If we want to have some feedback of the first wall with the plasma, then that can be done with codes like SolPS, but for larger tokamaks, the runtimes for these codes can range up to several months if you model ITER. And that means that running these codes is extremely expensive. And if we now want to tackle uncertainties in these codes, we have to take that into account. But also on a smaller scale, if we just look into some of the input data needed for these codes like SolPS, like sputter yield. So the first wall is subject to impinging fluxes. So there's hydrogen impinging onto the wall, and the wall then is being sputtered, which means that atoms are being sputtered out of the surface. And what you see here in that graph is the sputter yield, how many iron atoms are being sputtered per impinging deuterium atom as function of energy. What you see here are two code results. Blue is the code result from SWIM, and red code result from SDTRIM. These are well-known binary collision codes, which in principle incorporate the same physics, and superimposed on that, you see some experimental data. One data set from weight loss measurements and one data set from Rutherford backscattering. And in principle, we know a lot about the system, but there are still several input parameters which are uncertain in the experiment and also from the physics side. So in the experiment, we don't have precise access to relevant quantities like the angle of impact of the ions. We don't know atomistic quantities like what is the surface binding energy of atoms for such a disordered surface, what is the displacement energy. So the question which we face here is, we have codes which produce outputs, we have data with uncertainties. So which physics model is the correct one? Which of the two codes is correct, or are both correct within the uncertainties of the experimental data? Since these quantities are then used for lifetime estimates, it's relevant to see if, for example, the threshold, which we see for SWIM, which is significantly higher than for SDTRIM, does make sense, because that would extend the lifetime, or if the more, let's say, the worst prediction for the lifetime of SDTRIM is relevant. So how can we now address this problem of uncertainty quantification for computer codes? And one of the main tools for that is polynomial chaos expansion. From a global perspective of this uncertainty quantification, we have some random inputs into the codes. So input parameters where we don't know the precise value, so we are uncertain. Then we have some computational model, which is processing these uncertain inputs, and then eventually want to have some results, how reliable the results are, what is the scatter of the results, given that we have not only an imprecise knowledge about the input. And of course, we want to learn something from this. We want to know which of the input parameters are the most relevant ones, which combination of parameters cause the most consequences, have the most consequences for our computational model. Essentially, there are three main thrusts in this approach to uncertainty quantification. The first one is sampling. If you can afford it, that's the method of choice, but often it's too expensive. Then spectral expansion, polynomial chaos expansion, which I will spend some more time in the following, and then the use of surrogate models. As we have heard, this morning, especially Gaussian processes are suited for that, for a variety of reasons. So let's step into the first one, Monte Carlo approaches. Essentially, you have the input parameters, which are uncertain. If you can sample from these, then you just create a large set of samples, run your code for all these samples, and then you can compute all the resulting statistics of the code outputs, just averaging over the code outputs, and then you can compute the moments, the mean, the variance, and the higher order terms. That's straightforward, and it has a very big benefit. It includes all the correlations which are in the system. So essentially, it forms kind of a gold standard. The additional benefit is if you have the computational power, it is trivial to parallelize because you can use all the different codes simultaneously. And that's the drawback. Essentially, as with all the other Monte Carlo approaches, the accuracy scales only with the square root of the number of runs. And that means that to get a significant improvement in the accuracy of these moments, you need a lot of runs, which you typically cannot afford. The second drawback is now you have spent all these computational efforts to get the set of simulations. Then essentially you just have an unstructured cloud of simulation points, and there is not much you can do in terms of post-processing, because typically there, as we have heard also this morning, need some kind of space filling design, and this is something which you don't have here. So if you can afford it, Monte Carlo approach is perfect. Don't look further, but typically for more expensive computer models, you cannot afford it. So example for the case of the sputtering, we have three main parameters: the energy of the impinging ion, the impacting angle, and the surface binding energy. Parameters coming from the experiment. We have a Gaussian uncertainty on the energy of the impinging ion with a sigma of 20 eV. The surface binding energy is uncertain by about 0.4 eV, and the angle is also uncertain by about 4 degrees. And now we can plug that into our simulation codes, SDTrim and SWIM, and compute the sputter yield and the associated uncertainties. Since these codes are not very expensive, we can use 20 to the power of 3, so 8,000 simulation runs, where we sample from the distributions, and we get sputter yield for these conditions of 5% and some associated uncertainty of roughly 1%. That would be now our uncertainty given these experimental uncertainties. However, in practice, we cannot afford for more complex codes this large number of runs. So can we do better? And yes, we can do better using polynomial chaos expansion, which is kind of name dropping. This term dates back to Wigner in the 30s, and at that time chaos did mean something different from today. Nowadays one would label it just spectral expansion, but since it's a fancy name, it is commonly used. But actually spectral expansion would be a better description for that. So how does it work? We have our complex computer code, which has uncertain inputs, and these inputs follow some probability distribution. And if we now run our code, the code output will also have some uncertainty, will also have some probability distribution. And then it turns out that the code output, if the variance is finite, can be expressed as a summation of random variables, and that these expansion forms a set which is complete. And this is essentially the underlying concept of the spectral expansion that will become more clear in the next slide. So the obvious questions is, of course, which space shall be used for these random parameters? How can we compute these parameters? And how can we finally relate the computed parameters to something which makes some sense? Essentially, this is the key idea. So we have a random vector, m uncertain inputs into our code. That's given by a joint probability distribution f of x. Then this input distribution is modified by our code into an output distribution y. And then we essentially say, okay, we expand this response of the code in a spectral expansion. And the promise is that this can be done more efficiently than just by using Monte Carlo samples. The trick is how to choose now these basis functions so that only a small number of expansion coefficients is sufficient to describe the code output. The key idea is here, if we have some knowledge about the probability distribution of the inputs, then the code output is hopefully distorting this distribution, but not by much. So if we enter with a Gaussian distribution, then of some parameter, then maybe the code will produce some output, which is depending, let's say, like some power of the input. If we now consider what is happening to a Gaussian distribution on the input, then the output will be tilted because we, for example, have some squared of that, but it is still resembling to a large degree the input distribution. And that means that if we expand our output in terms of a function system which is suited to the input probability distribution, then we can restrict ourselves in many situations with only very few expansion coefficients. How do we compute these basis functions? Essentially, it turns out that for these integrations, which we have seen on that slide, so we have some probability distribution f of xi, and we expand that into basis function psi1, psi2, then it turns out that this can be computed efficiently with this three-term recurrence relation. For example, codes for that can be found in numerical recipes, and this is a numerically stable approach. However, we do not have to do that because it turns out that for the most common input probability distribution, these expansion classes of polynomials have all been discovered already centuries ago and have associate names. So if we have, for example, a parameter which has a Gaussian input distribution, then the orthogonal polynomial system which is suited for this weight function are the Hermite polynomials. If we have a uniform input distribution, then the corresponding expansion can be performed in Legendre polynomials, and so on. And essentially for each input distribution, it is easy to come up with the corresponding class of orthogonal polynomials. Okay, but now you may say we don't have a single polynomial, but we have input quantity, but we have plenty of them. Then, of course, we can just use a tensor product of these. So we multiply the individual expansion coefficients, and then the rest goes through without any changes. And that means that essentially the sum is running over the number of input parameters which are uncertain up to the expansion order which we're interested in. In principle, it's infinite, but the choice of the polynomials hopefully reduces the degrees of freedom. And here you see an example for 2 input parameters for the third expansion order. Here, Legendre polynomial on the x1 axis and Hermite polynomial on the x2 axis, and you see it's a pretty flexible set of basis functions. There's one design decision which has to be taken. The class of polynomials is given by the input distribution, but to which order we have to expand. In theory, infinite, but of course we can only afford a finite order, and typically the expansion orders are restricted to 3rd, 4th, or 5th degree. Beyond that, the number of terms which needs to be considered, which is given by the binomial factor of number of terms and the expansion factor over the expansion order, is just exploding. That means this is essentially limiting how far one can go. An explicit example for that, for example, we have 2 input parameters and expand these up to 3rd order. Then we have in total 10 terms, and the polynomial Karras expansion is essentially consisting of these individual expansion polynomials in the first parameter, in the second parameter, and in the cross terms. So for example, A4 correspond to 1st order in the polynomial in the first parameter and 1st order polynomial in the 3rd parameter, which you see here. It's just the product of the 2 parameters.
So can I interrupt you for a question?
Yes, of course.
In the previous slide, did that specify what kind of polynomials have been chosen, or is that still broad? Like when we talk about a polynomial, a chaos polynomial expansion, does that refer to, my question is a bit about the language. Does that specify what kind of what basis functions we have chosen, or is it a broad expression for all of them?
Yeah, so essentially it's deterministic. So given the probability distribution of the input parameter, the class of orthogonal polynomials is fixed because it has to be the class of polynomials which are orthogonal for this weight function, which is given by the input parameters. So here, this is Legendre polynomial. So this is essentially for a uniform parameter, input parameter. So, but this is deterministic.
Right. But what if the distribution that we're trying to reconstruct is none of these idealized known distributions?
So it's only on the input side. If you have some other distribution, so something which is not listed here, so could be some whatever, then you can easily derive the corresponding class of polynomials using this 3-term recurrence relation. So
I see.
So that's the so-called ASCII scheme, essentially, but that's standard numeric. So whatever you have as one-dimensional input distribution, you can come up with a corresponding expansion. So this is no problem at all. It's just that the most common ones have already been discovered a while ago.
So if your distribution were to have Gaussian-like features, but were not exactly Gaussian, the recurrence relation would not actually give you Hermite polynomials. It would give you something else that may have some. Okay.
But please remember, it's it's on the input side where you specify, and the input side then determines what is the corresponding polynomial expansion. On the output side, of course, it will be something different, but the hope is that this class of polynomials will need only a few terms to provide an accurate description of what the code did to the input distribution.
Okay, thank you.
Okay. So essentially now we have decided which expansion polynomial class we are using. The spectral approach classically had two main thrusts: intrusive approaches, which were mostly used by finite element codes, because as you will see in a second, there you need to rewrite the code, or what is used nowadays and much more recommended is non-intrusive approaches. In the classical intrusive spectral approach, as led by Josef Masuk from Max N 2012, essentially you plug in the expansion on the input side, the expansion on the output side, and then you project onto the same class of polynomials. The problem is that essentially you have to rewrite your code such that you can solve this projection. And of course, that's something which you do not want to do. The benefit would be you have to rewrite the code and the solution only once, and then you get these expansion coefficients essentially for free. But nobody essentially is nowadays rewriting the codes to do that. That was useful if the code class is mature and it does not change. So that means nowadays we have non-intrusive approaches, and essentially these consider the computational model just as a black box. So all you need to do to compute the coefficients is to run the computational model at a predefined set of input parameters. How does that look like? From the input distribution of the parameters, we know which class of polynomials have to be used. We have to compute the expansion coefficients, which essentially amounts to solving this integration. The expectation value of the output can be computed by the result of the code and the corresponding polynomial class weighted by the distribution of the input parameters. And essentially, this is the integration which needs to be solved. And essentially, we can now take advantage that we already know that our integration has to be performed with a weight function, which is given by the input parameters. And that means that we can adjust our numerical integration such that this integration can be performed most efficiently by individual evaluation of our code and corresponding weights. Essentially, what this amounts to is that you reformulate the necessary expectation integral in terms of a Gaussian quadrature, and surprisingly, it turns out that the weights and nodes of this Gaussian quadrature are precisely the zeros of the weight function system. And that means that with only a few points, we can achieve a very high degree of exactness. The polynomial which can be integrated exact is 2 times number of integration points, that -1. That means with only a few support points, we can get up to extremely high exactness. And that's the main benefit which we get if we use this approach. If we now have not a single parameter, but multiple parameters, then we have to use the tensor product for the integration. And this is, of course, cumbersome, because then the number of points for which the simulation code needs to be evaluated is increasing exponentially in the number of dimensions if we don't use additional measures. But the basic number which we need for if we use Gaussian quadrature is relatively limited. Essentially, the computational cost is order of the expansion to the power of number of input parameters. So here you see the exponential behavior. How does that look like for our example with the sputter yield? We have 3 parameters. We want to expand up to 4th order. That means that we have to use 5 points, 2 for 6 points, because 0th order is counting also. So in total, we have, instead of 8,000 simulations, we have only 216 at these lattice points. And the result is that we get 5% sputter yield plus minus uncertainty of 1%, which is a pretty good match to what we got from Monte Carlo simulations, but we needed only 1/40 of the total number of simulations. There is one additional benefit. Since we now have the coefficients of our spectral expansion, we have also a cheap surrogate model. So is everything solved? Unfortunately not, because if the number of parameters is increasing, then this tensor product, which we need for the integration, is exploding. And already for 10 parameters, we would need, for reasonable expansion orders, 1 million code runs. So that means the plain tensor product does not solve the day, but if you have only, let's say, 5 uncertain parameters, that's feasible. Can we do better? Yes, if we neglect some higher order interaction between the parameters, then the integration can be performed with much fewer support points, like Smoljak sparse quadrature rules, and we pay the price that the integration is not longer exact up to 2 times number of points, but only up to the number of points in the degree of the polynomial, but we need much fewer of these integrations. And this is quite significant. If we, in addition, use also nested grids, meaning that if we increase the order in an adaptive way, we do not have to recompute lower order terms, but can reuse them. And just to give you a number, if we now go to 10 parameters, then instead of 1 million runs, we can use, or it's sufficient to use 1200. And it's easy to code that because the necessary support points and weights are already tabulated. So this can be done right away. And here you see example for the full order. as what is plotted is on the y-axis the accuracy on a set of test points as function of the expansion order, and the full order you see is nicely decreasing. However, to get for the highest order the computation, it took about 40 days, whereas with the nested sparse grid and adaptive scheme, it was done within a quarter of a day. So if you have more than a few parameters, sparse nested grid is the way to go.
Udo, just to warn you that we've basically reached the end of the hour, so heads up.
Yep. Okay. I'm already coming. Yeah. So how do we exploit that? So now you have computed with some effort the coefficients, and what can you do with that? The nice thing is that with the coefficients, you can get a lot of useful information, because these coefficients not only form a surrogate model, but they also provide information about what is going on. Essentially, with a surrogate, you can now compute all the distributions of your model, how the density behaves, and that's really fast because you can sample directly from the expansion order. But more interestingly, you get the Sobel decomposition for free. What is the Sobel decomposition? Essentially, your complex code, the response of the code, can be decomposed into the contributions of the individual parameters, the contributions of the pairs of the parameters, and the contributions of higher order combinations of the parameters. So essentially that tells you how important the different parameters are, or combinations of the parameters. And this is, of course, a very important information. And how do you get these Sobel coefficient? Essentially, it's just a linear combination of these expansion coefficient. That will become more clear on the next slide. Sorry. If we do that for our example with the sputter yield, it turns out that the surface binding energy on the sputter yield is the dominating contribution, which contributes 70% of the total variance of the output of the sputter yields. That means all the other parameters are less relevant. And higher order contributions, so maybe some interaction between surface binding energy and impact angle or so, are absolutely negligible. So that means it's a very simple simulation in the end, since we know, have the information that it's essentially linear, can be very nicely decomposed into the individual contributions. Given that information, of course, one can design experiments to improve upon that. And it turns out that the most likely value for the surface binding energy, a quantity which is essentially not accessible by other means, has to be revised. And if one plugs that in, it turns out that SD trim is confirmed, and the SRIM simulation together with the uncertainties can be completely ruled out, because within the uncertainty of the simulation codes, the data cannot be explained by SRIM, but by SD trim. And that means, since we have now the uncertainties in the codes, the uncertainty in the data, we can say not only the parameters have to be different, we can also say the one code does not hold under the validation effort. It has to be ruled out. So do you have to program that on your own? No. Luckily, in the last years, there have been quite a number of software packages being developed, where essentially you just specify your input distributions, and then the codes the models will be distributed onto the computational resources you have, and the results will be computed. So Vecma, for example, is dedicated for exascale computing. So scalability is up to several tens of thousands CPUs. Dakota is also highly developed. UQ Lab is has a lot of very interesting tools. Chaos Pi gives you a hands-on approach onto these tools. So in conclusion, uncertainty quantification is now not only feasible, but should be done and yields you a lot of additional information, which is very hard to access otherwise. And that essentially concludes this part of the talk. Okay, so I would say, since we are at 9 o'clock, I will stop here and I'm ready for questions.
Okay, thanks, Udo. I'll check the Discord channel to see if there are any questions. And people can go ahead and unmute if they want to ask a question to Udo as well.
I'd like maybe to ask one question if there is, if I can. Udo,
Yeah,
could you please summarize, basically, if I had a complex code, let's say SOPS, which was mentioned in the talk, and I wanted to create a surrogate model of some sort, basically, how would I go about using these sparse coefficients and these libraries that are already doing much of the work? Could you please summarize what would be the workflow like?
Okay.
Very broad question.
Yeah, so so essentially these packages for uncertainty quantification consider the code as a black box. So essentially you say how many uncertain parameters you have. Let's say the ones which you're interested in, let's say 7 uncertain parameters. They ask you what are the distributions of these parameters. Maybe temperature is 1 keV plus minus 100 eV Gaussian distributed, or maybe density is between 5 times 10 to the 19 up to 7 times 10 to the 19 uniform distributed. So you have to specify these distributions, and then you have to specify what is your computational resources. So how many CPUs you have available, and then essentially these codes pre-compute at which parameter settings you have to run the code.
Okay, so could you clarify what is the downside of these methods with respect to sampling schemes that may use MCMC, Hamiltonian Monte Carlo, nested sampling? If I want to just use these pre-computed grids, am I getting a significant gain with respect to a method that goes and explores the entire distribution directly?
Okay, so what you get is the response around, let's say, the default parameters. So you have, let's say, some mean value and some uncertainty. And you get the response function given that the parameter has this mean value and some spread. The code does not explore what is happening in other stages. So with the nested sampling and other approaches, you essentially follow a trajectory, but you do not take into account that you have this joint input distribution. These, the UQ approach, the PCE, takes into account what is tries to summarize the code response in the most efficient way. If you just apply MCMC, you do not get this information compression.
It's not obvious to me why the full information about the chains in MCMC or similar methods, why those wouldn't hold the entire information about the interactions between the various parameters. Can you please expand?
So you would need a much larger number of simulations. So I've shown you that with the sparse grid, you need 1,000 simulations, so 1,000 individual runs to get a response in 10 dimensions. If you do MCMC in 10 dimensions, with 1,000 simulations, you would not even be within the warm-up phase of your MCMC code.
Okay, so where you're sacrificing, so maybe it's correct to say that the sampling is the full approach and we're looking for a reduced model in some sense, a reduced way of approaching the problem. But what we're sacrificing is the full knowledge of all the states that could be explored by direct sampling. Is that correct?
I think so these methods, let's say, have different directions or targets. What you try with the polynomial chaos expansion is you want to summarize the response of the code in as few parameters as possible by carefully selecting the basis function in which you expand the response, and you try to do that efficiently by neglecting higher order interactions. And that allows you to, instead of having 1 million code runs, you have 1,000. With MCMC, you eventually get the full information, even if there are higher order ones, but typically it would involve so many code simulations that you would never get there in the first place.
But just to be clear, in the expansion, you don't have to specify what are the basis functions, right? These open source packages that you were indicating, they do
that for you. You specify only the input distribution.
Right,
the
so
output distribution is deterministic in that sense.
Okay, so you basically specify the priors and your simulation model.
Correct.
Okay, thanks a lot.
There is one drawback, because I was always saying the input distribution determines the output. This is only possible in a straightforward way if the input parameter distributions are uncorrelated. This is very often so, but if they are correlated, you have to use some Nattav or Rosenblatt transformation before to decorrelate them. This is often possible, but not always.
So I can relay a question from Discord. What if one cannot assign a probability distribution to a parameter because there is not enough knowledge about it?
Okay. The thing that you run your code for some parameter already implies that you have some knowledge. It's a computer code. It requires some input. If you have absolutely no knowledge, then I could say just run 10 to the power of 1 million or so. Then you would say, no, that's not possible because the computer code does not digest that, which very strongly implies that you have already some information about the scale of the parameter. If you have some information about the scale of the parameter, you can specify some min-max values and use Jeffreys prior or something else. So I can hardly imagine that you have a computer code, an operational computer code where you don't have any idea about the magnitude of the parameter. And what will be the outcome if the magnitude of the parameter does not affect the result? Then not to some extent, it is only weakly interacting. If it affects the results, which the output will tell you, then you know that if you match that with the experiment or some observations, you already get some insight about the magnitude. So in both cases, you have learned something.
Makes sense. Before I relay you another question, there was a more procedural one. And so if you could send us these slides, I can upload them on the shared Dropbox folder. So if it's okay with you, and then so people can, participants can look back at those topics. And if they have additional questions, then just drop them in the chat or send you an email. And then one last question. You mentioned uncertainty in temperature as an example. Do things become more complicated when you deal with distributions, such as particle velocity distributions, which may themselves be uncertain?
So the question is, if you do not have individual parameters, but maybe functions, essentially what you do, you expand these functions also so that you then get back to a finite set of parameters. So yes, can be done. Essentially, if you have something like density profiles or temperature profiles, essentially each profile amounts to something like 3 or 4 parameters if you do the expansion.
Right.
So can be done.
Okay, I think, yeah, both. All right, I think we satisfied the questions that I saw on Discord. Is there any other question? Okay, since we are quite beyond the hour, I would thank Udo again for his availability and for sharing this lecture with us. Thank you for joining also at a late hour and for being a speaker at our school. And yeah, I'll call it a day, and I'll see you all tomorrow for the last day of the school.